Okay, so 2 more lessons left in this semester. Lesson 30, a lot of conceptual stuff. It's the effusion, diffusion, kinetic molecular theory, which is often abbreviated KMT, because kinetic molecular theory is a lot to write each and every time. So you really just need to go back and read, make sure you understand definitions, think of some examples that make this more concrete in your mind and not as abstract. We're going to go through all the pre-lectures and then the 3 questions at the end, because there's really just not all that much in this lesson or in the next lesson. So, I won't say in the next one, but it does kind of slow down at the end, because you should be looking towards exam 4 and the cumulative ACS final exam. Okay, so these things are on the horizon for you. So what is the difference between diffusion and effusion? So the difference between, in my own words, is that diffusion is that molecules are dispersing in space, and not like outer space, but in a specific space, a container. They're dispersing. So the room you're in, okay? So a room. Effusion, on the other hand, is where molecules are passing through something. Through a small opening, so through a barrier of some sort. So, i.e., a balloon. It would help if I could spell balloon. Balloon. Hopefully that's right. Looks kind of weird to me right now. Okay, so that's my definition. Okay, your book is going to give you another one, but when I have to compare the two for my self, I like to think of it as one dispersing through space, like within a room, and one is passing through a barrier, like a balloon. So what are the factors that affect the rate of diffusion? So how quickly diffusion, which we've clarified up here, occurs. So some of the factors are concentration gradient. So you've probably learned about concentration gradients, like pH gradients, maybe in biology, and maybe in other classes like A&P classes. But concentration gradient is kind of like if I have an area of high concentration and an area of low concentration, the rate of diffusion is affected by this gradient. Okay, if it's equal and equal, there's no gradient there for gas to diffuse either which way, because they're equal. They're at equilibrium. So when things are not at equilibrium, like a teeter-totter, a seesaw, then we have movement, because things are not equal, and they are going to move until both sides are equal. The second is the surface area. And then distance, because we're looking at the rate, how quickly. Okay? So these are our factors that will influence the rate of diffusion. Okay? Your book does a really great job of illustrating these for you with really specific examples of how they will change, how the rate is influenced due to these factors. Okay? What does Graham's law of effusion, so we have to think back to what we said about effusion, predict about the rate of the effusion of gases? Okay, and in a nutshell, what Graham's law predicts about the rate of effusion is that as the molar mass of the gas increases, the speed of effusion decreases. Okay, so they are inversely related, meaning heavier gases will travel more slowly. Okay? And then vice versa is true. The lighter gases will travel more quickly. Okay, so that should help with the Graham's law of effusion. All right, so in your own words, summarize the 5 postulates of the kinetic molecular theory, which is KMT. So for this, I want to open up OpenStax. There it is. I have to flip it this way. I still don't quite understand why it doesn't work in the other direction. Okay, so we are in chapter 9. Uh-oh, not what I meant to do. There it is. And we just talked about the effusion and diffusion, so I want to show y'all the spots where it talks about diffusion and effusion, and it gives you an example of all of that. Okay, and then the kinetic molecular theory, all I'm going to do is, in my own words, I'm going to summarize the 5 things that you see here at the top of the page, where it says that gases are composed of, and it gives you 5 things. Okay, so I'm going to take these and then put them into my own words. So your words may be different than mine, and that's okay. So my first takeaway is that gases are always moving. Okay, so that's my first one. My second one is that the gas molecules, and that's what I mean when I say the gases, I'm talking about the molecules themselves. The gas molecules are really far apart, meaning there's more space between each gas molecule than the space that the actual gas molecule takes up itself. If that weren't the case, it would be really difficult to walk in the classroom because you would have to literally be basically breaking through the gas molecules to move. But because they're really far apart and they occupy a very small space with respect to the room that they're in, the container they're in, we are able to move quite easily through a room. Okay, the third one, if you think back to that Khan Academy video that that you were shown at the intro to pressure, it talked about what pressure comes from. So pressure comes from the gas molecules colliding. So you remember the balloon example? He drew the balloon and then it was this POW in yellow that showed that that's the collision, right? But then that's going to happen continually. They're all colliding, and they're all colliding in different ways at different times. The fourth postulate, my takeaway was that there are no attractive or repulsive forces between these gas molecules. Okay, so in theory, no attractive or repulsive forces between gases. The fifth one is important because it's going to relate us to kinetic energy, and that's that the kinetic energy of the gas will increase as the temperature increases, and then vice versa. So as we heat up a system and we increase the temperature, the kinetic energy of that particular system will also increase, and then we have this I would say it's an equation that comes from physics because that's when I remember learning it specifically, but it relates kinetic energy to the velocity, which is the speed. So then we can say that as the temperature increases, the kinetic energy increases, and the velocity, or the speed, of the gas also increases. Okay, so we get all 3 of those through the kinetic molecular theory, the KMT. Okay, again, make sure you are reading the book. This does not replace reading the book. There's a lot of important information in there that you can get just through reading it, so I'm not going to regurgitate that information for you. But make sure you're reading it to get your own interpretation of these things that we just talked about. All right, so we're supposed to give 2 examples that clearly distinguish between effusion and diffusion. And I like to have examples because sometimes an example takes something that seems abstract and makes it into a concrete piece of information because we can relate it to our everyday life. So my first thought of effusion is a balloon deflating. This is always really heartbreaking to my son because we buy balloons that are filled with gas that floats, therefore the balloon floats. So we get a helium tank, we fill up the balloons, they float. The next day, or depending on the balloon, because some balloons hold helium better, longer. So foil balloons do better than the actual like rubber balloons at holding the helium. But the next day, maybe 2 days later, the balloon stops to float and now starts to sink, and that is effusion. The helium is seeping out of the balloon. The foil balloons have a better protection of effusion from happening, so the helium's not escaping as fast, whereas the rubber balloons are more porous and the helium can escape a lot quicker. Okay, so that's one example for effusion. Now diffusion is you wake up in the morning and maybe you're at home, because I know that most of you don't have kitchens in your dorms. If you do, you probably are not getting to make something like bacon. But maybe you're at home and you wake up to the smell of bacon or coffee, and that is diffusion. Okay? So smelling bacon in your room in the morning. Okay? It's probably not being cooked in your room. It's being cooked in the kitchen. Because the smell is traveling, that process is called diffusion. It's not going through a barrier per se. It's just traveling through the air from an area of high concentration, high bacon smell, to low bacon smell, which is your room. For me, it would be coffee, though I do like bacon too, but coffee is better. Okay, so those are my 2 examples that I use to help solidify these 2 terms in my mind. All right, so which of the following gases diffuse slower than oxygen? Okay, so there's a trick here, a small one, and that is that we have to remember that oxygen is a diatomic. It does not exist by itself, okay? So in order to answer this question, we have to compare the molar masses. So what I'm going to do is I'm going to calculate the molar masses of these. Okay, so fluorine has a weight of 19. When I have 2 of them, that is a weight of 38. I think I need to give myself a little bit more space. My handwriting is too big. Okay, so then we have neon, and neon has a molar mass of 20. When we have dinitrogen monoxide, this is going to be 14 times 2 for the nitrogen plus the 16 for the oxygen, and this is 44 grams per mole. My acetylene, 12 times 2 plus 2 is 26 grams per mole. Nitrogen monoxide has a weight of 30. Chlorine, 35.45 times 2. So remember, this is one that's kind of strange to round up or round down. So I leave it as 35.45. And then we have H2S, which has a weight of 34 grams per mole. Okay, so we need that information first. So now what I have to think about is what I said before about diffusion as it related to Graham's law. Okay, that's why we defined that earlier. So Graham's law predicts that as the molar mass increases, the speed of effusion will decrease. And it also is true about diffusion. The things that are lighter will go faster. The things that are heavier will go slower. So in this case, I need to find things that are heavier than oxygen. I want to, darn it, sorry. highlight. If I want to find things that will diffuse slower than oxygen, they need to be heavier than oxygen. So given that piece of information, I need those weights I just calculated. So F2, heavier. 20 for neon, it's not heavier. Dinitrogen monoxide is heavier than O2. C2H2 is not heavier. Nitrogen monoxide is not heavier. Chlorine gas is heavier, and so is H2S. These are all heavier. Okay, so that should answer that question. If I was asked the opposite, at what is lighter, I would have picked neon, C2H2, and NO. Okay, so pretty straightforward. I could really see this as a multiple choice question on not only exam 4, but on the final ACS exam. They love things like this because you have to know how to calculate the molar mass as well as apply these rules about the Graham's law and things like that that are up here in the rate of diffusion. Okay. All right. The last question says, using the postulates of the kinetic molecular theory, explain why a gas uniformly fills a container of any shape. Okay, so I'm going to take you back to OpenStax because I want you to see that there's some extra stuff in here. Okay, so if you keep reading down, it's going to explain how the kinetic molecular theory relates to those individual gas laws we've already talked about. Okay, so I would recommend reading through this because it's going to show you how well that they do complement each other and how that they explain each other. Okay. Okay, I think that's all I wanted to show you on that one. So let's go back. And using the postulates, explain why a gas uniformly fills a container of any shape. Well, the first thing is that the first rule I said is that gases are always moving. So because they're always moving, it means if I have different types of gases, because they're always moving, they are basically going to evenly distribute themselves in any container. Okay, they're not going to settle out like a homogeneous solution. Because they're always moving around, they will uniformly distribute themselves. Okay, so that's what we needed to say. It's uniformly distributing. And it doesn't matter the shape of the container. If I put it into an Erlenmeyer, I never do very good at that right-hand side and making it symmetrical. Okay, you're not going to have a pocket of this gas here and this gas over here and then like this, okay? Because they're always moving around, the gas molecules will evenly distribute themselves. The second thing that we have to accept to be true is that the gas molecules will mix without any attractive or repulsive forces. I need to make this more clear. Sorry, repulsive forces. Okay, if gases mixed, or if gases were susceptible to attractive and repulsive forces, the scenario on the right would be what we would see, because maybe the green here doesn't, it's actually repulsed from the pink gases, and then maybe the blue gases exhibit a strong attractive force for each other. So we have to accept that the gases do not have an attractive or repulsive force present, therefore they will mix evenly. Okay, let's see where we are. So we have 1 and 4. Okay. So the third one is that the pressure that the container is under occurs from constant collisions, which really goes back to number 1 here, that they're always moving. So the pressure from constant collisions is a result of the number 1. Okay? Therefore, the pressure should theoretically remain unchanged if we don't change anything else about our system. Okay? The other thing is that the kinetic energy is related to temperature, which is related to velocity. So as long as we hold the temperature constant, the kinetic energy should be constant, and the velocity should be constant. Okay? And then the last one is the space between the molecules, and that really goes back to number 2. So the space between the molecules is very large because number 2 is true. They don't exhibit any attractive or repulsive forces in the container. Therefore, they will evenly distribute themselves to maximize that space, and then they are randomly colliding at all times. They're colliding with the sides of the container, they're colliding with each other. All of those things are contributing to the overall pressure of the system, which is constant, because we don't change the temperature, we're not changing the velocity, and we're not changing the kinetic energy. Okay, so we are coming from a lesson, 2 lessons where we have a lot of math, to a lesson where we have a lot of conceptual information, and then we're going to end on a lesson that will be more math, but really we're not adding a whole lot of math. We are just adding an extra formula, which is going to be called the van der Waals equation. Okay? All right, I hope that all is well. This lesson should be more than short enough that you are able to spend time asking Dr. Spencer or Dr. Morris questions about the exam, about homework, sapling problems. Do not leave the lecture room if you are in any way confused or concerned or worried. This is the time to address those things, because we are nearing the end of the semester, and once that happens, it ends very quickly. So please make sure you are communicating with them, or communicating with me. Send me an email. I will get back to you as quickly as I can. But I hope that all is going well for y'all this semester, and I look forward to seeing y'all in the spring.